All right, y'all. Today I'm going to be talking about the first fundamental theorem of calculus. And what that is, besides sounding like the most important thing you've learned so far in calculus, is it is kind of the foundational piece of integration. It's how we actually integrate. So far, we've been estimating integrals with Riemann sums. We found specific areas under the curve, which were integrals, but of nice shapes that we could evaluate. Then we found indefinite integrals, anti-differentiation. So we actually found out how to go backwards in our calculus process by integrating instead of deriving. And now we're going to kind of put that area under the curve and that indefinite integration together and find the area under specific curves of all different types of functions that don't form nice, pretty areas by using the fundamental theorem of calculus. So it states that if f is continuous on the closed interval a to b, and capital F is the indefinite integral of f on a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So just to kind of lay that out, we're integrating the function f of x. So we're finding the area under the curve f of x from the x interval, in this case, because it's dx, of a to b. So it's like our geometric area, except this isn't going to be a nice, pretty shape. Okay, or we can do it for nice, pretty shapes as well, but this works for any curve. So that's, fundamental theorem of calculus is kind of that next step up because it always works. Capital F, of course, is the antiderivative. It is the integral. So f of x is the original function. Capital F is the integral. So I'm finding the integral, capital F, and then I'm plugging in b, and I'm plugging in a, and I'm doing f of b minus f of a. So I'm finding that difference between those two values, which should give me the area between the curves, okay? And those are our two steps. So anti-derive or integrate, and then evaluate f of b minus f of a. So we're going to find our integral, and then we're going to plug in b and a and subtract them. Pretty straightforward, yeah? That's the fundamental theorem, most important thing in calculus. Okay, so let's look at an example. Example 1, we have the integral from 1 to 2 of x squared minus 3 times dx. So we're going to integrate first. So from our integration rules that we should already know, or at least remember, x squared becomes x cubed over 3 minus 3 becomes 3x. And then instead of plus c, because it's a definite integral instead of an indefinite integral, we have that interval and it's going to move to the back with this new notation. So we're evaluating it from 1 to 3. So that straight line instead of the integral symbol, because we've already integrated, so we don't want to still have the integral symbol there and confuse ourselves. This is the notation anytime you're doing the fundamental theorem of calculus. It's what you're going to see online. It's what you'd see in your textbook, on the AP exam, any steps that get explained to you. This is that notation. Okay, so x cubed over 3 minus 3x, that is our antiderivative or our integral. 1 to 3 is the interval we're going to be evaluating at, a to b. So then we want to plug in b and plug in a, and we're going to subtract those two. So I'm just going to start plugging it in, a. As I go across, everywhere there's an x, I plug in my value. So first we get 3 cubed over 3 minus 3 times 3, then minus 1 cubed over 3 minus 3 times 1. Okay, notice how the second piece, my a, I put in parentheses because I need to make sure I subtract the entire value of capital F of a, not just put a subtraction sign in the middle. So that parentheses helps to note that I need to distribute the negative to both. And then I can just start simplifying from here. So 3 cubed over 3, that's 20. Well, y'all, I don't know why I keep doing this. This is the second time I record this, but I keep saying the interval changes to 3. It's not an interval of 3. It's from 1 to 2. So ignore me being absolutely crazy and just plug in 2 in the front. Okay, regardless of that, so 2 cubed over 3 is 8 thirds minus 3 times 2 is 6. Then minus 1 cubed over 3, that's 1 third. And 3 times 1 is 3, but minus makes a plus, so plus 3. Okay, so 8 thirds minus 6 minus 1 thirds plus 3. And I can just keep simplifying from there. So 8 thirds minus 1 third, that's 7 thirds. Negative 6 plus 3, that's negative 3. Then I can change negative 3 to be 9 over 3. So 7 thirds minus 9 thirds is equal to negative 2/3. And that is our area under the curve. Okay? Because remember, that's what we're doing with the fundamental theorem of calculus. We're finding the area under our curve or under our function, f of x. So it's like if this was I'm going to do a really rough sketch of our graph. Well, not exactly a 2. So if this was our curve, and I'm going from 1 to 2, it's this little area right here and right here. Okay, so that's what we found. We found the area under the curve, just like we've been doing before, but as the name curve implies, it's a curvy little shaped area. So those aren't nice, pretty triangles that I could just do a geometric formula for. So that's why they had to come up with the fundamental theorem of calculus. It is the full process of integration. Okay, so let's look at some more examples. So number 2, we have the integral from 1 to 4 of 3 times the square root of x times dx. Okay, so once again, I want to integrate. Before I can integrate the square root of x, though, I do need to change that into x to the 1/2. So this becomes the integral from 1 to 4 of 3x to the 1/2 dx. Okay, so now I can evaluate that by doing my reverse power rule. So 3x to the 1/2 is equal to 3x to the 3/2 divided by 3/2. I'm evaluating that from 1 to 4. And before I still even plug in, remember dividing by 3/2 is the same as multiplying by 2/3. If I multiply by 2/3, those 3's are going to cancel out. So I get just 2x to the 3/2 power. And I'm still evaluating it from 1 to 4. Okay, so now I just need to plug in. So this becomes 2, 4 to the 3/2 power, minus 2 times 1 to the 3/2 power. Notice how I didn't have to put parentheses around the whole second piece this time because there's only one term to my function. So I didn't have to put parentheses. But if it makes yourself happier, put parentheses so you don't forget. Okay, now at this point you might be like, Mr. Ibone, how are we going to evaluate a 3/2 power? Well, remember, a 3/2 power is just a compound power. The bottom means to root, the top means to do a traditional power. So this is the same thing as square rooting and cubing. Now you can do a compound power in any order. So I could cube first and then square root, or I can square root first and then cube. So I always choose to make the number smaller if possible and then make it bigger. It makes it a little easier to work with. So what is the square root of 4? 2. 2 cubed is 8. So 2 times 8 minus square root of 1 is 1. What's 1 cubed? 1, which 1 to any power is always going to be 1. So 2 times 1. So this is equal to 16 minus 2, which is equal to 14. And that's it. Okay. So pretty straightforward. Integrate, plug in the numbers, evaluate from there. Okay. Not so crazy steps. The only thing we've added new is the plugging in the numbers, the f of b minus f of a. We've done the integrating before. We did that with indefinite integrals. So let's keep working a few. So number 3, we have the integral from 0 to pi over 4 of secant squared x times dx. Okay. So this one looks crazy, but it's a pretty simple integral. So what is the integral of secant squared? Well, that is tan. So this becomes tan of x evaluated from 0 to pi over 4. So this is just equal to tan of pi over 4 minus tan of 0. Tan of pi over 4, that's sine over cosine. So root 2 over 2 over root 2 over 2, which is just 1. So 1 minus tan of 0, sine over cosine. So 0 over 1, which is just 0. So 1 minus 0 is equal to 1. Oh, sometimes trig comes out to such pretty answers. Okay, and last but not least, we have the integral from 0 to 3 of x minus 1 times dx. Okay, but absolute value, because remember, those straight lines means absolute value versus traditional parentheses. Okay, so you might be thinking right now at this moment, oh, well, that's just x squared over 2 minus x, and then you evaluate. Well, what about those absolute value signs? Well, we actually don't have an integration or a derivative rule for absolute value signs. We've never dealt with them before. Okay, so because we can't actually integrate them traditionally, we have to think about what is the shape of this function that we're actually integrating. So I'm going to take you over to our graph real quick. All right, and I'm going to go ahead and graph x minus 1 so you can see this. All right, so this is our graph of the absolute value of x minus 1. So notice if you take the inside of the absolute value signs and solve it for x, it gives you where the point of that absolute value is going to be. And then it's just two linear lines from there that make that sharp point. Okay, so from 1 moving forward, this is the line x minus 1. Remember, if it kept coming down, it would go all the way down here to negative 1. Okay, from the other side, the left side of our absolute value curve, remember, absolute value makes any negative y values become positive. So it essentially takes a linear line and reflects the negative portion of it up over the x-axis. So instead of this part being x minus 1, this is actually negative x because it has a negative slope plus 1. So the other half of an absolute value sign, of an absolute value function, is just the negative version of whatever is in the absolute value signs. Okay, so x minus 1 is my right half, negative x plus 1 is my left half. Well, I can use this information to actually integrate an absolute value function. So remember, my integral properties allow me to split up an integral at any point along its interval. So I can split up that integral from 0 to 3 into 0 to 1, 1 to 3, 0 to 2, 2 to 3, 0 to 0.7 to 0.7 to 2 to 2 to 3. I can do whatever I want. I can split it up as many times as long as I'm still integrating the same thing. So likewise, I can split this integral of the absolute value of x minus 1 into the integral from 0 to 1 of negative x plus 1 dx plus the integral from 1 to 3 of x minus 1 dx. Okay, so a couple of things, because you're probably like, whoa, you blew my mind, Mr. Arbone. So I split it at 1 because that is where the break happens in my absolute value function. So if I'm looking at this triangle from 0 to 1 and this triangle from 1 to 3, the break happens at 1. So I want to integrate from 0 to 1, then I want to integrate from 1 to 3. Okay, negative x plus 1 is the interval from 0 to 1 because that's the curve that is represented here. Negative x for the negative slope plus 1 for the y-intercept. X minus 1 is the integral from 1 to 3 because that's the curve that is represented here. X minus 1 would be this line that goes all the way down if it was to continue through negative 1 as its y-intercept with a slope of 1, and it goes from 1 to 3. Then for the total area, I still want to add both of those two integrals together, so that's why I have a plus sign in the middle. I'm adding those two integrals together. Okay, so from here, now I can do my fundamental theorem of calculus. So integral of negative x plus 1 would become negative x squared over 2 plus x, and I'm evaluating that from 0 to 1, plus the integral of x minus 1 would become x squared over 2 minus x. And I'm evaluating that one from 1 to 3. Okay, so notice once again, anytime I have a multiple term equation, I want to put parentheses around it so I make sure that I just note that that whole thing is being evaluated. So from here, I can start plugging in. So negative x squared over 2 becomes negative 1 squared over 2 plus 1 minus, something I want you to notice, if every term in here has an x, I'm about to plug a 0 in, what's that 0 going to do to everything? Just going to make everything 0.
If you have e-lunch, please.
So anytime you're plugging in 0 and every term in the function has an x in it, then you can just plug in 0. A little less work for you. Then from here, 3 minus 1, so plus 3 squared over 2 minus 3 minus 1 squared over 2 minus 1. And then I'm just evaluating from here. So the biggest thing, y'all, when you get these longer fundamental theorem of calculus questions is being very mindful and careful with your positives and negatives. Okay, you really, really, really got to pay attention. So 1/2, negative 1/2, plus 1, that 0 is just gone, plus 9/2 minus 3, minus 1/2, plus 1. Okay, so from here, negative 1/2, negative 1/2, 9/2, that becomes 7/2. 1, 1 minus 3, that becomes just minus 1, which minus 1 is negative 2 over 2. So 7/2 minus 2/2 would just equal 5/2. And that is your answer. Okay. Now, you might be like, Mr. Darbone, that is so long and I would never have time for that, yada, yada, yada. Well, the good news about absolute value functions, y'all, is once again, on the AP exam, the expectation is never going to be that you have to show all of these steps. There's lots of ways for you to solve things. So if you can sketch the absolute value of x minus 1, you can also just use the graph, because on this graph, you can very easily see that it's a smaller triangle or a bigger triangle. You can sketch a graph and use what you know about geometric area to just say, well, it's going to be the area under this triangle and the area of this triangle added together, which would be 1 times 1 times 1/2, so 1/2, and then 2 times 2 times 1/2, which would just be 2. So 2 plus 1/2 is 5/2. So you can use it graphically. That's why we learned how to find these graphically, or you can do the full process and do it using the fundamental theorem of calculus. Either way, I don't care how you do it as long as I see the work for one or the either. I can't see no work, but I got to see one or the other, okay? So let's keep moving on. We've got just a little bit more to do for today's notes. All right, number 5, find the area of the region bounded by the graph. F of x is equal to 2x squared minus 3x plus 2, the x-axis, and the vertical lines x equals 0 and x equals 2. Hey, this is a really fancy way of just telling you to do the fundamental theorem of calculus, because it's the same question, but it just hasn't written the integral for you. So let's write our integral real quick. So our function is 2x squared minus 3x plus 2. We're integrating from 0 to 2. And it's over the x-axis, so it is dx. Okay, so that just looks like any other fundamental theorem of calculus question. So we're going to integrate, and then we're going to evaluate our fundamental theorem. So this is equal to 2x cubed over 3 minus 3x squared over 2 plus 2x, evaluated from 0 to 2. So then I want to plug in 2 and then plug in 0. Good thing about plugging in 0, everything's got an x in it. So this becomes 2 cubed over 3 minus 3, 2 squared over 2 plus 2 times 2 minus 0 because the other side's 0. That's awesome. So this becomes 2 cubed times 2, that's 8 times 2, so 16 over 3. 2 squared is 4, divided by 2 is 2, so this becomes 6, plus 2 times 2 is 4. So then 16 over 3 minus 6 plus 4, minus 6 and plus 4 becomes minus 2, so 16 over 3 minus 2, which becomes 16 over 3 minus 6 over 3, which is just equal to 10/3. And yes, y'all, I do realize you can type these in your calculator, just like you could type this whole thing, and your calculator will actually evaluate the fundamental theorem of calculus for you. But I need to see the steps because you won't have that same calculator resource for the AP exam. So you need to be able to do these by hand. That's very important. Okay, very last thing we're going to talk about, and actually we've done it before. Okay, the shaded region A has an area of 9.3. And the integral from 0 to 6 of f of x dx is equal to 6.1. We're going to use this information to fill in the blanks. So 6 through 11 are actually the same integral property questions we've done a bit before. But now we do actually know how to evaluate if we're integrating the function. So we can actually make some things a little bit easier. But anyways, so number 6, we want to know the integral from 0 to 3.5. Well, 0 to 3.5 is the area of region A, and the area of region A is 9.3. So 6 is just 9.3. Pretty simple. Number 9 is the integral from 3.5 to 6 of f of x. Well, 3.5 to 6 is just this negative area right here. And if I know the entire area is 6.1, then the area from 3.5 to 6 has to be whatever made 9.3 go down to 6.1. So that would be, looks like negative 3.2. Okay, because 9.3 minus 3 would give you 6.3 minus 0.2, 6.1. So there we go. All right, number 6, I want the area from 0 to 6 of the absolute value of f of x. So the absolute value, remember, that's going to make any negative area become positive area. So all of a sudden, this negative 3.2 from 3.5 to 6 becomes positive 3.2. So 9.3 plus 3.2 for my total area would become 12.5. All right, number 10, I have the integral from 0 to 3.5 of negative 3 f of x dx. So that negative 3, it's a constant being multiplied. So when I integrate it, I ignore it and multiply my final answer by that number. So we already know the area from 0 to 3.5 is 9.3, so I just need to do 9.3 times negative 3, which would be negative 27.9. Okay, nice and simple. Same idea on number 8, 3.5 to 6 of 4 times f of x dx. So I'm doing the area from 3.5 to 6, which I already know is negative 3.2. So negative 3.2 times positive 4 is negative 12.8. Okay. So far, pretty straightforward. Last but not least, number 11, I have the integral from 0 to 6 of f of x plus 3 dx. Okay, so this one, I have an addition sign, so I can split this up into the integral from 0 to 6 of f of x dx plus the integral from 0 to 6 of 3 dx. Okay, integral from 0 to 6 of f of x dx, we already found that. That's 6.1. So this is 6.1 plus, before I would think about this geometrically. I think of 3 as the horizontal line, y equals 3. But now I can actually integrate this. So this becomes 3x. I'm evaluating it from 0 to 6. So 6.1 plus 3 times 6 minus 0, which 3 times 6 would be 18. So this becomes 6.1 plus 18, which is 24.1. All right, y'all. And that is all for our fundamental theorem of calculus. So notice, as you probably did there at the end, that as we go through these, our integral ideas are starting to kind of overlap with each other. All of these different things are just a lot of different ways to tackle the same idea of area under the curve. So some of our ideas and some of the things you've learned are going to start to overlap and kind of start to feel similar. And when you get to questions on like a test, it's not going to be clear like, oh, this is indefinite integration or this is geometric area, yada, yada, yada. You just kind of have to have all these tools in your tool belt and you can use them whenever you need them. But with that being said, this is day 1 of Fundamental Theorem of Calculus. We will do the second page of these notes next class, so don't worry about them for right now. And I hope to see you in class. All right.